Alright, so this is Griffiths Electrodynamics problem 4.2. What we're talking about here is the polarizability of a hydrogen atom. So if you, just to review, the definition of polarizability is if we have some external electric field and we want to find the dipole moment of an atom. Right, these are going to be proportional, and the constant of proportionality alpha is the polarizability. All right, and you can call these vectors as well. In our case, we'll just be looking at the magnitudes. At any rate, the charge density for just the 1s orbital of the hydrogen atom, so the ground state, is given by this equation right here. All right, and we're going to use this to try and estimate this alpha. If you look at example 4.1, you'll see something similar, except rather than using the fancy quantum mechanics version of the charge density, we actually use just a constant charge density, a sphere of constant charge density. But the argument goes like this. So if we have an atom, which we'll just model as a positive charge inside a uniformly distributed electric charge, negative charge, electron, right? Proton in the middle, electron around the outside. Whether we're calling this a uniform density or the actual density, what's going to happen is when we put this atom in an external electric field, right, the positive charge is going to move relative to the negative charge. The way I'm going to draw this is, let's just use a frame of reference where the negative charge we'll just say that stays in the same place, and just the positive charge it moves. All right, so in the influence of this external electric field, the positive charge is actually going to move some tiny distance. This is greatly exaggerated, right? It's going to move some small distance. We can call that d. All right, and kind of the way we'll approach this problem is this positive charge is going to stop moving when the electric field, due to this distributed negative charge, will cancel out the external electric field. All right, so if you can kind of picture, I'm not sure if I can draw this in. Let me just draw a dotted line right here. What we're going to do is use Gauss's law to find the electric field due to the negative charge inside this Gaussian surface. All right, this is basically the same as I'm sure we've done the problem where you just have you're finding the electric field as a function of position as you move radially outward through a uniformly charged dielectric sphere, something like that. All right, this is the same sort of thing. So let's go ahead and set this up. So just using Gauss's law, right, we just have an E dot dA, that sort of thing, is equal to the enclosed charge divided by the permittivity of space. All right, so in this case, E dot dA, right, this E dot dA is going to, we're integrating over the surface of this Gaussian surface in here. All right, that's a radius of d. So this is a 4 pi d squared. All right, so that's just the surface area of this Gaussian surface. All right, it's just analogous to this, well, it's the same thing as using Gauss's law for this charge density here before, finding the electric field, you know, at some point inside of a uniformly charged sphere. Same sort of thing. The one difference is we're not going to call it a uniformly charged sphere. We'll call it this S orbital equation right here. All right, so here's the part where we use that. We have to integrate the charge density to find the enclosed charge right here. All right, so I'm going to bring my 1 over epsilon naught out front, and we're just going to do the integral in 3 dimensions of a sphere. All right, so 3 dimensions. I'm going to go ahead and put in our, well, for now, let's just write the charge density as a function of r, right? And let's just use d tau for a second, just to call this our volume integral, right? We're going to do this integral in spherical coordinates. Much nicer that way. All right, let's talk about the limits of integration of this. It's just, let me write this out real quick so we know what order we're, dr, d theta, d phi. All right, so working from the outside inward, d phi is the azimuthal angle, right? Goes from 0 to 2 pi. D theta goes from 0 to pi. And then dr will go from 0 to d. All right, we're integrating the whole charge inside of this sphere. All right, now we also have the Jacobian, which for the spherical coordinates, let me just put an arrow right here, okay? This is an r squared sine of theta, the Jacobian for spherical coordinates. All right, so a really good thing to memorize, I'm sure you have it down already, is this sine of theta integrated from 0 to pi, it just gives you a 2. And then this phi integrated from 0 to 2 pi, right? That's the only phi in this whole part here. That gives you, of course, 2 pi. So the sometimes people will write these 3 things right here as just a big omega. All right, it's just like a solid angle, that sort of thing. All right, so we have 4 pi over epsilon naught, and all that's left is our radial integral. We're going from 0 to d, and we have an r squared, and then this rho of r, which we need to plug in, dr. Okay, our rho of r is right here. All right, let's go ahead and plug that in. So, should we go ahead and divide by this? Let's go ahead and divide. So we'll just have an e on the left-hand side, and on the right-hand side, I'm going to divide by this, right? So 4 pi d squared, and then we have our 4 pi over epsilon naught. All right, now we have our integral here, but we know there's going to be some constants mixed in this q over pi a cubed, so let's bring those out front too. All right, these are just the constants that are inside of this row. Now let's write our integral from 0 to d. We have an r squared, and then we have our exponent from this row, which is right here. E to the minus 2r over a dr. Okay. So the idea here is we're solving for this e. Once we solve for that, and we're going to use the trick that Griffiths describes, where we expand we'll end up with a factor of this. We'll expand that. Anyway, once we do all that, we'll find p within that expression, and when we divide p by e, that will give us alpha, our estimate for the polarizability of the atom. All right, this integral can be done by integration by parts. All right, I'm going to go ahead and do that. There's also nifty formulas you can look up that just, you just match up the parts. And all right, so skip ahead if you've got the integration by parts down. It's just good to review it once in a while. For now, let's write this out. I'm going to keep a 4 pi epsilon not out front. That leaves a 4q, and then we have d squared a cubed. All right, I think I did that right. All right, and then we have our integral here. Let's just okay. Great. Let's do this integral. I'm just going to do an indefinite integral first, and then once we figure out the answer to this indefinite integral, we'll put in our limits of integration. All right, so if you've got this down, skip this part of the video, skip to the skip the whole integration part. All right. So I'm going to be using the integration by parts formula. So how do we do? Let's call this u dv is equal to uv minus v du. Okay. So in this case, u is equal to r squared. dv is equal to the e to the minus 2r over a dr. So this gives us a du equal to 2r dr. And integrating this, we get, let me draw a line here just so we keep these separate. Integrating this, we get a minus a over 2 e to the minus 2r over a. All right. So now, let's keep in mind what we've got here. Here's our r squared e to the minus 2r over a dr. And right now, so that's this piece right here. Now we need a uv minus integral v du. So uv are these two pieces, right? So minus a over 2, and then we have our r squared e to the minus 2r over a. And then we have a minus v du. So there's this minus sign that gives us a plus a over 2, and then we have a 2r, and we have this e to the minus 2r over a, and this is a dr, and this was all an integral. All right, now we need to do integration by parts again to get this integral right here. So let me just write out another integral. We'll have to kind of keep track of this, and then we'll put all the pieces back together. All right, these are just constants, right? This 2 is going to cancel out, and we'll just get an a here. So we have an r e to the minus 2r over a dr. So I'm just going to use u and v once again. All right, it's similar to what we did over here. U this time is just equal to r, du equal to dr, and dv equal to e to the minus 2r over a dr, and v equal to, again, minus a over 2 e to the minus 2 r over a. All right, so let me just write it up here. This integral is equal to, now we have our uv, so we have a minus ar over 2 e to the minus 2r over a minus the v du part. Again, we have our minus sign here, so that gives us a plus a over 2, the integral of e to the minus 2r over a dr. Okay, so this is a big mess. I hope this is, anyway, sometimes it's easy to get rusty on integration by parts and stuff, so it's good exercise, I think. And then this integral, so let's let me just put an arrow up at this one and an arrow up at this one, just so we remember this equation, and now this one, we have an a over 2, and then the integral of this is just itself with a minus a over 2. Okay, let's see if we can put the pieces back together. All right, so let's go ahead and write this one out again. So we have an r e to the minus 2r over a dr is equal to this right here, minus ar over 2 e to the minus 2r over a, and then we are putting in this piece right here, this last integral that we did. That's a minus a squared over 4 e to the minus 2r over a. Let's simplify it down really quick, just to, if we're lucky we'll save a little time later. There's obviously an e to the minus 2r over a that can be factored out. Well, what else? Well, let's call this a minus e to the minus 2r over a. And then we have, yeah, I guess I won't factor the whole thing out. This a squared over 4. All right, so remember what we did. We just plugged this last piece into here and got the answer for this. Now we need to plug this piece in to here. Much faster to just look up that equation. So what I've done now is I've taken this equation right here and written it again down here to remind us what we're plugging in. So here I'm copying from up here. So minus a over 2 r squared e to the minus 2 r over a, and then now what did we have here? It was just this integral, except remember these 2's canceled. It was just multiplied by an a. So that integral is right here, and the answer is right here. So we just have to add this on, but multiply it by an a. Let's write that down here. Minus a e to the minus 2r over a, and then this ar over 2 plus a squared over 4, like so. All right, so now we are up to this stage right here, which is right here, and that is what gets plugged in right here. So now we can write back to E. Okay. Yeah, we'll just write 4 pi epsilon naught. We have a 4q, all right, copying from up here. 4q over d squared a cubed. And then we have our integral that we just found right here, but it's evaluated from 0 to D. Let me write that in right here so I don't have to write it all out a bunch of times. We have a couple minus signs here. So what I'm going to do is call this a plus and a plus, okay? And then I will go from D to 0. All right, so first when we plug in a 0, we see here that this R is going to make this term go away. All right, plugging in 0, that goes away. And this R is going to make this part go away. So when we plug in a 0, oh, by the way, e to the 0 up here, that's just going to give us 1. So all that we have left is this a, and then this a squared over 4. So our first limit of integration just gives this a multiplied by this, which is an a cubed over 4. All right, now we subtract. I'm going to end up factoring out this e to the minus 2r over a. All right, so I'm going to subtract yeah, let's put this in another set of parentheses. All right, we have an a, and then we have a d squared over 2. Okay. And then this minus sign came out, so we're still, anyway, we still have a plus sign. You can do your own algebra, because I obviously am having trouble. So we have a plus a squared d over 2, and then plus a, that's an a cubed over 4, and then these, these three terms are multiplied by our exponent, e to the minus 2r over a. All right, and then we have our closed parentheses from this one right here. All right, let's write this out. Shall we? Shall we write this out one more time? We can factor out an a cubed over 4. You see that here and right here. And so that will simplify things a little bit. And then we get to the fun part where we are going to do the expansion of the exponential. All right, so I am factoring out an a cubed over 4. That gives us a 1 here, minus, what does that give us? That gives us 2 on top and an a squared and a d squared on top. Okay, plus a 2d over a from this term, and then this one is nice and easy, it's just a 1. Okay, and then of course our e to the minus 2r, oh excuse me, this is a 2d now, isn't it? Because we were plugging in our limits of integration. 2d over a. All right, and then we have a closed bracket, or brace, or bracket. So I think we're good up to this point. I think so. One thing we can do is cancel out this 4, and we can cancel out this a. All right. So the big hint Griffiths now gives us is expand this exponential. So we're assuming d is very, very small compared to a. What is a? A was the parameter right here, which is, it's basically, I think, the radius of, well, it's what, like the board radius or something, right? So the atom's all fuzzy, but if it has a radius, the Bohr radius, right? So the positive charge relative to the negative cloud is getting shifted, but only by a very, very, very tiny amount relative to the size of this cloud. So that's why we're going to do this expansion. D over A is very small. Okay, let's write this out one more time just to clean it all up. We have a 1 over 4 pi epsilon naught, as always. All that's left up here is a q over d squared. And then we have a 1 minus, we've got a 2d squared over a squared, plus a 2d over a, plus 1, and then an e to the minus 2d over a. All right. Let's draw a line here to keep these separate. All right. So what we're going to focus on now is only the piece inside these brackets. Let's go ahead and look at the infinite series expansion of e to the x. All right, this can be written, I can write a sigma here, as an n, a sum over n from 0 to infinity of x to the n over n factorial. Okay, so we are going to write out the first 3 terms of this sum, and that's all we're going, anyway, that's going to give us the first term that doesn't go to 0. So that's all we're going to need for our approximation. All right, so e to the minus 2d over a is going to be approximately equal to, all right, so starting off with n equals 0, all right, something to the 0th power gives us a 1, and then 0 factorial is defined as 1, so we start with a 1, all right, next term in the sum. The n is now equal to 1, so again, 1 factorial on the bottom is still 1, but now we have minus 2d over a. All right, you can write a 1 here if you want. Now let's go for the, okay, I lied, we're going to take 4 terms, not 3, I think. Okay, so now for the third term. So now n is equal to 2, so we have a minus 2d over a to the 2nd power now, and then our 2 factorial is just 2, all right? All right, and I can write a factorial here if that helps us remember what we're doing. And then finally, let's go ahead and do the 4th term, which is n equals 3. So we have a 3 factorial on the bottom now, and we have this minus 2d over a now to the 3rd power. All right, this obviously, if we want the exact, not the approximate, then this series will just go on forever. But we are only going to take these first 4 terms. Let's go ahead and write them out properly. So we have a 1. Okay, this minus sign is going to stay, so minus 2d over a. And then this minus sign gets squared away. And then 2 factorial is just 2. That's going to divide out with one of these 2's. All right, so we just have a plus 2d squared over a squared. And then this time we'll have a minus sign because it's a minus to an odd power. So now we have an 8 on, so 2 cubed is 8, and 3 factorial, 3 times 2 times 1 is 6. So we have an 8 divided by a 6, or in other words, a 4 divided by a 3. And then, of course, d cubed and an a cubed. All right, these are the only terms we're taking, so here's our approximate sign. So now we're going to go back and look at the term inside the brackets. All right, so if I look only at this factor inside the brackets, right? Let me write that out. 1, and then, yeah, I'm going to keep the minus sign here. So we have and I'm going to reverse the order just to maybe make things easier to multiply out. 1 plus 2d over a plus 2d squared over a. All right, and then this part is multiplied by our exponential, which we are approximating by this. All right, again, we're only looking at the term inside the square brackets. So now I write the approximation for our exponential, 1 minus 2d over a plus 2d squared over a squared minus 4 thirds d cubed over a cubed. All right. I think this is all that we needed. I don't think we need to write any more terms of this. I guess we'll find out. So let's go ahead and write this out. We have a 1, okay, and then let me go ahead and write this minus sign inside these parentheses. So let's multiply minus 1 by this. So we have a minus 1, so basically we'll write this out with a minus sign in there. So minus 1 first, and then a plus 2d over a, and then a minus 2d squared over a squared, and then a plus 4 thirds d cubed over a cubed. Now we're going to take this term and multiply it by this and write it in there. Minus 2d over a. That's this, all right? And then we'll have a plus, which is a 4d squared over a squared. And then, I'm continuing down on this line, we have a minus 4d cubed over a cubed. And finally, a plus 8 over 3 d to the 4th over a to the 4th. Okay, and then finally this one, multiplying this and this, minus 2d squared over a. Something's not right. This needs to be squared, right? Our units need to work out here. Let me just double check if I can find where did we, yeah, right here, right? A squared on the bottom. That was this one multiplied by this one. All right, now we've got a plus 4d cubed over a cubed, and then minus 4d cubed, or sorry, to the 4th power over a to the 4th power, and then a plus 8 over 3d to the 5th over a to the 5th. All right, so some of these terms are obviously going to be ignored. So let's see what we get first. Let's see what cancels out. This will divide out or subtract off with that. Let's look at the d's. How about just the d over a's? All right, so here's a d over a. There's a 2 and a minus 2. Now looking at the squared power, we have a minus 2, a plus 4, and a minus 2. So these two are going to kill this one. And then finally, So here's a 4, sorry, a minus 4 of this d over a cubed, and a plus 4, so these two are going to die. All right, so the first term that does not get completely killed off are these d over a cubed. All right, and this one's going to be much larger since d over a is so small. It's going to be much larger than all of these other ones. So this is the only term that we are keeping. All right, so remember what we were doing. We were looking only at that term in the brackets. So if I can dig through all this stuff and go back and find that. Here it is. All right, so let's write out E again. And when we come to this term in the brackets, we'll just plug in what we found right here. So we have a 1 over 4 pi epsilon naught. I mean, I guess this should be approximately, since we're doing that approximation now. Q over d squared. Now we come to the term in the brackets. And we're just going to plug in this. So 4 thirds d cubed over a cubed. All right. Let me just see. Is this all, or did I? Let me double check this because I think these d's ought to cancel out. So I may have made a mistake somewhere. Let me see if I can find that. All right. Well, like Einstein's cosmological constant, our one mistake was thinking we made a mistake. This actually is okay. The units do work out. All right, so what happens is this d squared will leave us with just 1 power of d on the top. We can kill our beloved 4 in our 4 pi epsilon naught just this once. And we are left with qd over 3 pi a cubed epsilon naught. All right, so one thing that we need to recognize is qd is our dipole moment, the magnitude of the dipole moment. All right, and that's true of dipole. And anyway, Griffiths had that section about it doesn't matter where you put the origin for the, at least only for the dipole thing. You can just say qd for these 2 point charges. Anyway, this is equal to the magnitude of our dipole moment, 3 pi a cubed epsilon naught. All right, let's find a nice clean spot to write our final victorious answer, because if I can, here we go. Okay, here's our first page, way back when. If you'll remember, we wanted to find alpha. That's what we wanted to find. So here we have E equal to this P over this thing, right? So if I'm looking at this right, alpha should be right here. Is that right? Because I can write this as E equals P over alpha. So here's the E, here's the P, here's the alpha. So let's write it right here, nice and big. Alpha is equal to 3 pi a cubed epsilon naught. Okay, and you can compare that to example 4.1. Let me see if I can grab that real quick. Yeah, so that example just has a 4 here instead of the 3. All right, so if we were to use a uniformly charged sphere rather than the actual charge density of the 1s orbital in hydrogen, we'd get a 4 here instead. All right, and again, all of this was only to get a theoretical prediction or approximation for the polarizability of the hydrogen atom, which, as the book says, we get within a factor of 4 or something like that. So it's not great, but it's pretty good, I guess. So anyway, all that work for such a simple little answer.